Children, I hope you have gone through my previous video, and today we will continue further. Today in the chapter Chemical Bonding, we will study about formation of covalent bond by overlapping of atomic orbitals. We will start with valence bond theory. Now, according to Hitler and London in 1927, the presence of one or more unpaired electrons in the valence shell of an atom is the cause for chemical bonding. The postulates of valence bond theory, they say, first point is that every atom has a tendency to pair with its unpaired electrons, with oppositely spined electrons of other atoms. Second is that half-filled atomic orbitals of two atoms with their opposite spin properly align themselves and proceed to overlap. Third postulate is that overlapping of atomic orbitals of various atoms gives rise to formation of covalent bond. Fourth is, greater the extent of overlapping of atomic orbitals, stronger is the bond formed. Okay, so these are the postulates of valence bond theory. Now, covalent bonds, they are of two types, sigma bond and pi bond. Sigma bond, it is a bond which is formed by head-on overlapping of half-filled atomic orbitals along the internuclear axis. It may involve SS, SP or PP overlapping. See here, this is SS overlapping along the axis, along x-axis. S and P overlapping along x-axis, and this also P and P overlapping. Two P bonds, they are overlapping here. So this type of a bond is called as sigma bond. It is a strong bond because the extent of overlapping is large. Shape of molecule is determined by these bonds. Next is pi bond. Pi bond is not horizontal overlapping, but it is a type of bond which is formed by sidewise overlapping of half-filled atomic orbitals in a direction perpendicular to the internuclear axis. You can say that along y-axis. So it involves PP overlapping. It is a weak bond. See here, this is a p orbital, this is also a p orbital. It will overlap like this. So the overlapping is here and here in the perpendicular direction. So this is the overlapping. It is a weak bond because extent of overlapping of atomic orbital is very small and they do not affect the shape of the molecule. Now let us study first a few examples. First, the formation of hydrogen molecule. Hydrogen, you know, has only one electron. So it has one electron. Another hydrogen atom, it has one electron. They combine together to form H2 molecule. So this has upward spin, so the other electron will have downward spin. So they need to, the combining electrons, they should have opposite spins. Similarly, oxygen, O2 molecule. This is the oxygen atom. 1s2, 2 electrons in S. 2s2, 2p4. So 2 here, 1 and 1. 2 in 2px, 1 in 2py and 1 in 2pz. This is another oxygen atom, 1s2, 2s2, 2p4. Now see, till here, the electrons are paired. So these will not take part in bond formation. But these unpaired electrons, the 4 of them, they will take part in bond formation and they will combine together. So they will form O2 bond. Now in these, one will be a sigma bond and one will be pi bond. Now next is polar character of covalent bond. Now a non-polar covalent bond is formed between two similar atoms having same electronegativity or zero electronegative difference. For example, H2, O2, F2, Cl2, etc. And they are called as non-polar molecules. A polar covalent bond is a bond which is formed between two dissimilar atoms, in which one has high electronegativity and the other has low. Like for example, HF, H2O, NH3, they are all polar molecules. Greater the electronegativity difference, more polar is the bond. Percentage of ionic character in polar molecule, it is determined by Hannay and Smith by the formula percentage ionic character is equal to 16 epsilon A minus epsilon B plus 3.5 epsilon A minus epsilon B whole square. Alright, so this is the formula which gives you the percentage ionic character in a covalent bond. Next we come to dipole moment. Dipole moment is given by a symbol mu. This is dipole moment. The magnitude of polarity of a molecule is expressed quantitatively by its dipole moment, which is equal to amount of charge. Amount of charge is given by Q on either end of molecule multiplied by the distance between the charges. Distance is given by D. So mu is equal to Q into D. As Q is in the order of 10 to power minus 10 ESU and D is in the order of 10 to power minus 8 centimeter, mu is in the order of 10 to power minus 18 ESU centimeter. Dipole moment is measured in dB unit, capital D, that is the unit. So 1 D, 1 capital D is equal to 10 to power minus 18 ESU centimeter, which comes to 3.33 into 10 to power minus 30 coulomb meter. Dipole moment is indicated by an arrowhead, okay, pointing towards the more electronegative atom. Whichever atom is more electronegative, the head of the arrow will be pointing towards that side. Dipole moment of a particular covalent bond in polyatomic molecule is referred to as bond dipole or bond moment. Bond dipoles can be treated as vectors, and the polarity of molecule is predicted by taking the vector sum of bond dipoles. Now let us see the calculation of resultant bond moment. See here in this figure, let AB, this is AB, and AC, this is AC, be two polar bonds inclined at an angle of theta degree. This angle between these AB and AC is theta degree. Their dipole moments are mu1 and mu2. Mu1 is of AB and mu2 is of AC. Now resultant dipole moment can be calculated using vectorial method, which is given over here by the formula mu r is equal to square root of mu1 square plus mu2 square plus 2 mu1 mu2 cos theta. This is the formula. Again I am repeating, mu r is equal to, r is the resultant dipole. It is equal to mu1 square plus mu2 square plus 2 mu1 mu2 cos theta. When theta is 0 degree, the resultant is maximum. So mu r becomes mu1 plus mu2. When theta is 180 degree, the resultant is minimum, and mu r becomes mu1 minus mu2. Now what is the use of this dipole moment? Applications of dipole moment. First is to decide the extent of polarity in covalent bond. Now the greater the magnitude of the dipole moment, greater will be the polarity of the bond. Molecules which have zero dipole moment, they are non-polar, and those having mu not equal to 0, they are called polar. This is the first application. Second is Dipole moment is used to determine the percentage ionic character. Percentage ionic character, it can be calculated by the formula experimental value of dipole moment upon theoretical value of dipole moment into 100. Then the dipole moment can also be used to predict the shape of molecules and the symmetry of molecule. If a molecule contains similar atoms linked to central atom with polar bonds, the net dipole is 0, and it implies that the shape of molecule is symmetrical. Like here, see, in CO2, central atom is carbon, both side you have oxygen, so the net the dipole moment of this bond and this bond will cancel each other, net dipole will become 0. So this is symmetrical. Same over here, BF3, center atom is boron, sides may you have the same atom fluorine, net dipole will come to 0. So it is symmetrical. CH4, carbon is the central atom, hydrogens at the corners, so again it is symmetrical. In molecules where there are 3 or more atoms or 2 or more polar bonds, if dipole moment is 0, it implies that the shape of molecule is unsymmetrical. Like if you take water, water has oxygen and then both side hydrogen. So water does not have straight structure, it has a V-shaped structure because its dipole moment is 1.84 D. Similarly, SO2, sulfur dioxide, sulfur is the center atom, on the sides you have oxygen, but the dipole moment is not 0, it is 1.60 D. Okay, so it also has a bent structure. Similarly, in case of ammonia, NH3, and ammonia, it has pyramidal structure because along with these 3 bonds, there is also lone pair electron present in nitrogen, which is not taking part in bond formation. And CH3Cl, methyl chloride, dipole moment is 1.86 D. It is a triatomic structure. It has 3 hydrogen atoms and 1 chlorine. Dipole moment is 1.86 D. Dipole moment is also used to distinguish between cis and trans isomers. Cis isomers have higher dipole moment than trans isomers. In some cases, dipole moment of trans isomer may be 0. For example, in 1,2-dichloroethene, this is 1,2-dichloroethene. In cis isomer, dipole moment is 1.9 D. For trans isomer, the dipole moment is 0. So you can distinguish the 2 forms by seeing the dipole moment. Next application of dipole moment is to determine orientation in benzene ring. Now, greater the dipole moment, greater is the asymmetry. In general, dipole moment follows the order. Ortho compounds, they have greater dipole moment than meta compounds, and then para. So like you can see over here, this is an ortho compound. Ortho means the atoms are added on the first and second carbon of the benzene ring. So here the dipole moment is 2.54 D. The dichlorobenzene. Here again this is meta dichlorobenzene. So here attachment of chlorine is to the first and the third carbon. That is why it is meta. Dipole moment is 1.48 D, less than ortho. And in para, where the attachment is on the first and the fourth, dipole moment is 0 because it is symmetrical. So para compounds have the least dipole moment. Next we come to covalent character in ionic compounds. This is also called as polarization. Now polar covalent compounds like HF, H2O, NH3, HCl, etc. They have some ionic character. Similarly, there is some covalent character present in ionic compound. In ionic compound, cation attracts electrons of anion. Cation is smaller and anion is bigger. Why? Because in cation you have lost electron and in anion you have gained an electron. So anion is bigger in size. So in ionic compound, cation attracts the electrons of anion towards itself and repel its nuclear charge. The net result is distortion of or polarization of anion, and the ability of cation to polarize the nearby anion is called its polarizing power. And the tendency of anion to get distorted from its shape is by the cation, that is called as polarizability. Polarization causes sharing of electrons between two ions to some extent and develops some covalent character in them. See, this is smaller one is cation and this is anion. So when they combine together, instead of the spherical shape, now the shape becomes something like this. It gets distorted. So this is because of certain covalent character in ionic compound. The magnitude of polarization, it is determined from Fazan's rule. Polarizing power is given by ionic charge upon radius square. Formula of polarizing power is ionic charge upon radius square. Magnitude of polarization is given by Fazan's rule, which says covalent character in ionic compound is large when both cation and anion have high charge. For example, AlCl3 has more charge, more polarizing power compared to MgCl2. Why? Because Al has plus 3, Cl3 minus 3. MgCl2, Mg has plus 2 charge, Cl2 minus 2. And this will be greater than NaCl, where Na has plus 1, Cl is minus 1. Cation, if cation has small ionic radius, then also covalent character in ionic compound will be large. For example, in case of lithium chloride, the covalent character will be more in lithium chloride compared to sodium chloride. If anion has large ionic radius, that means lithium iodide will have more covalent character compared to lithium fluoride, because iodine is having a larger size compared to fluorine. Out of two ions having same size and charge, the ion with pseudo noble gas configuration will have higher polarizing power than noble gas configuration. What is the meaning of pseudo noble gas configuration? That is, ion having 18 electrons in outermost shell will have more polarizing power than noble gas configuration. In noble gas configuration, ion has only 8 electrons in outermost shell. For example, CuCl will have more polarizing power compared to sodium chloride. Polar medium keeps away the cation and anions, thus prevents polarization. So example, AlCl3 is a covalent molecule, but if you put it in water, water is polar, so in water it will behave as ionic compound. Okay. Now next is valence shell electron pair repulsion theory, which is also in short known as VSEPR theory. Now this theory was given by Gillespie and Nihon. First point of this theory is that the central atom in molecule can have paired as well as unpaired electrons. Paired electrons, they will exist as lone pair, and the unpaired electrons, they are utilized by atom to form bond. So they are called bond pairs. Both lone pairs and bond pairs are collectively known as electron pairs. Second point of VSEPR is that due to similar charge, electron pairs repel each other. This force of repulsion is not of equal magnitude. It is of the order lone pair repulsion is greater than lone pair bond pair repulsion, which is greater than bond pair repulsion. So least repulsion is between bond pair, and maximum is in lone pair. Third point is every molecule has a tendency to acquire a state of minimum energy. And this is possible only when the bond pair as well as lone pair, they are at a maximum distance from one another. Fourth point of VSEPR theory is the relative arrangement of bond pair as well as lone pair decides the geometry of the molecule, because it provides the minimum energy to the molecule. So the geometry is of two types according to VSEPR theory. First is the regular geometry. So VSEPR theory says that a molecule will have regular geometry if repulsive interactions among the electron pairs are of equal magnitude. That means, first point is that the central atom should be bonded to similar atoms. Like in case of CO2, central atom is bonded to similar atoms, oxygen this side, oxygen this side. Second point is the central atom is bonded to other atoms by similar types of bonds. So if there is a double bond here, there should be a double bond towards this side also. Third is there is no lone pair present on central atom. See, on carbon there is no lone pair present. And fourth is all bond lengths between central atom and bonded atom is the same, because they are the same atoms bonding same type of bond, so bond length will be the same. So CO2, BF3, CH4, they are all having regular symmetry. Second type of symmetry is irregular symmetry. Irregular geometry. This is also known as distorted geometry. Molecule will have irregular geometry if central atom is not bonded to similar atoms. Okay. Example, CHCl3. They are not bonded to similar atoms. Then central atom has one or more lone pair of electrons, like in case of ammonia. There are similar atoms, hydrogen, but there is also a lone pair. The central atom may be bonded to similar atom but has different bond lengths. Okay, like in case of PCl5. Central atom is bonded to other atoms by single as well as multiple bonds, like in SO3. Other examples are like H2O, NH3, etc. So let us take a few examples. First, we will study about shape of ammonia molecule. In ammonia, nitrogen is bonded by 3 bond pairs and 1 lone pair. Okay. Now, according to VSEPR theory, lone pair bond pair repulsion is greater than bond pair. So the molecule has irregular geometry. It has pyramidal shape with a HNH bond angle which is equal to 107 degrees. Other example of this type of geometry is H3O plus, NF3, etc. Second, let us take an example of water molecule. Shape of water molecule. Now in water molecule, central oxygen atom is surrounded by 2 bond pairs and 2 lone pairs. It makes 2 bonds with hydrogen bond pair, and 2 pair of electrons do not take part in bond formation. There are 2 lone pairs of oxygen present. So it should have tetrahedral geometry, but according to VSEPR theory, as the lone pair repulsion is greater than lone pair bond pair repulsion, which is greater than bond pair repulsion, water molecule has a bent or angular, or you can say it has a V-shaped geometry. HOH bond angle is 104.5 degree. It has less bond angle than ammonia because water molecule experiences more repulsion due to presence of 2 lone pairs, whereas in ammonia there was only 1 lone pair. Alright, So in this way, if the lone pair is present along with bond pair, there will be irregular geometry. Is it clear? So just revise what you have been taught today, and in the next video we will continue.